With the advancement of physical AI, the importance of devices for interacting with the real world has been increasing. Among these devices, various types of grippers have been studied to enable interaction with physical objects. Grippers composed of mechanical joints offer high payload capacity. However, precise force control is essential to prevent damage to fragile objects. To address this, soft grippers that leverage the elasticity of materials have been developed. These can reduce the pressure applied to objects and enable the grasping of delicate items. However, they typically have the disadvantage of low payload capacity. Therefore, it is essential to develop a gripper that can provide sufficient payload for handling most everyday objects, while also allowing flexible adjustment of the applied pressure as needed. Introduce compliant finger gripper called CFG. The compliant finger, made of two CFRP plates, bends like a finger through linear motion. The actuator generates linear motion with help from a LM guide and deforms the compliant finger. This transforms it from idle state to grasping state to holding an object. This single finger is assembled with a yaw joint and can be used as a finger of a gripper with multiple fingers. This is the simplified schematic of the single compliant finger part. Each plate is made of 0.5 mm thick carbon fiber reinforced plastic, and the basic hole-to-hole distance is 150 mm. Based on this, 4 design parameters that are expected to affect performance were selected. First, omega is the vertical separation, meaning the vertical distance between the entry points of the two CFRP plates. Second, theta is the entry angle, meaning the reference angle at which each plate is attached at the entry point. Third, gamma is the thickness ratio, meaning the width ratio between the two plates. For example, if the thickness ratio is 2:1, the lower plate have 20 mm wide and the upper plate have 10 mm wide. The average width of two CFRP plates are fixed at 15 mm for set the average stiffness of the finger constant. Finally, phi is the exit angle, meaning the fixed angle at the end tip of the compliant finger. This shows a table of the design parameters. The 4 3-level parameters represent the key design parameters that define the structure of the compliant finger. Considering when user control as a gripper, the movement position of the linear actuator D was used as a user condition. The movement position of the linear actuator D reflected the driving range of the maximum linear actuator possible by design. These are samples according to the design parameter for better understanding. As shown, the shape of compliant finger in the idle state change depending on the parameter values at each level in the table. In particular, in models B and C, the different plate widths make the compliant finger deform into an asymmetric shape. This is the test bench used in the experiment. The sample finger mounted on the bench is deformed into a specific shape by the slide, which moves according to the user condition D instead of a linear actuator. At this time, the deformed sample finger generates a reaction force when it contacts a pad driven by a screw and motor. This reaction force F was measured using a load cell. The experiment measured the reaction force F as the compliant finger deformed when contacting a pad driven by the motor and screw. Measurements were repeated 3 times for each of the 3 user conditions. The highest force measured by the load cell was defined as F max, and this F max was used to calculate the SN ratio, as larger the better. This is the orthogonal array based on 4 3-level design parameters. The experiments were conducted according to the combinations in the array, with a total of 9 tests in the first experiment. Instead of testing all 81 combinations of the 4 3-level design parameters, the Taguchi method was used to reduce the number of tests to 9 and find the optimal values. These are the average values from the repeated tests in the first experiment, and calculated the SN ratios as larger the better. A higher value means a result that better meets the objective. This is the sensitivity analysis graph about design parameters from the first experiment. The graph shows that the optimal values are gamma of 1 to 2, omega of 30 millimeters, theta of minus 30 degrees, and phi of 15 degrees. It can be seen that gamma shows high sensitivity, while the other three parameters have similar sensitivities. The high sensitivity of gamma may have reduced the apparent sensitivity of the other three parameters. The range of second experiment's design parameters were based on the results of the first experiment. It focused on a narrower range near the optimal values of the three design parameters, omega, theta, and phi. Showed similar sensitivities, although gamma showed the highest sensitivity. It was fixed at 1 to 2, the optimal value from the first experiment due to design limitations. These are the average values from the repeated tests in the second experiment, and the sensitivity analysis graph about design parameters. The optimal values were omega of 35 millimeters, theta of minus 35 degrees, and phi of 7.5 degrees. Additionally, as shown at the combined graph of the first and second experiments, the difference in SN ratio by parameter greatly decreased in the second experiment compared to the first are shown. This suggests that the optimal parameter which obtained from the second experiment reached close to the optimal point. Therefore, we determined the final optimal parameter based on the result up to the second experiment. The final optimized design parameters are gamma, the thickness ratio of 1 to 2, omega, the vertical separation of 35 millimeters, theta, the entry angle of minus 35 degrees, and phi, the exit angle of 7.5 degrees. Compared to the basic design, the maximum holding force, F max, increased by about 2.2 times. Compared to the worst design combination which obtained worst result from the first experiment, which was experiment number 3, F max increased by about 6.3 times. This is the prototype of the compliant finger gripper, made of 3 optimal compliant fingers grasping objects. It shows the gripper grasping an onion, an oriental melon, and a potato. It's shown that the CFG supports and lifts the object from below without applying strong pressure or force other than the contact itself. The optimization of the compliant finger was performed to lift heavy objects. To test this performance, we performed lifting tests with heavy loads. A CFG can lifts a 2 kilogram counterweight of balance, and a 2 plus 1 kilogram combination of counterweight of balance. Also, CFG can grips and lift off the narrow neck ring of a 2-liter bottle filled with water. Therefore, the CFG can be fully utilized for devices that require high payloads with a concise structure.